Induction is the third method of charging an object. And it's when an object becomes charged from another object, but they don't touch. Let's take a look at this example. We have two objects, they are both neutral. Over here we have a negatively charged object. When we bring this negative ball close, it's going to induce the electrons in object A and B to move to the right, because the negatives do not like negatives. So the electrons move from here to over here. They're induced to move to get away from this negative. Because the materials are conductors, the electrons can move through as though they're one big material. And there is an overall positive charge on this side and negative charge on this side. So the item is neutral but polar. The reason why it's still neutral is because you still have 8 negatives and 8 positive protons. So it's still neutral, it's not charged, but it is polar. This means we have not charged any objects yet by induction. What we have done is cause polarity by induction. At this point, the polarity can be reversed if the negative charge is moved away. So the object, which is a conductive material, the electrons can flow back and forth to neutral and then polar. If we want to charge this object through induction, we must separate the objects at this point. Once the objects are separated, they are no longer reversible and they both have a charge. These electrons would reorient themselves to be farther apart from each other. At this point, we have charged two objects by induction, and the negative balloon can be moved away and their charges will remain. The next method of charging something is called grounding. Grounding is actually the removing of a charge, usually. So the definition is removing excess charge by transferring electrons to or from a large object. So like Earth, and that's why they call it grounding. So in the end, what grounding does is usually it makes something neutral, usually. I'll show you an example. So here we have a negative object. We have 4 pluses and 8 minuses. We have these extra red minuses here, these electrons. If we wanted to get rid of them, we could ground this object. And the way you would do that is by literally touching the object to the ground with, for example, a copper wire. This is the symbol for grounding. Just to be clear, it is this upside down kind of arrow. The electrons, as you can see, want to be as far away from each other as possible. And as soon as they have the option of going somewhere else, they're going to take it. The ground has an infinite number of pluses and minuses, and it can absorb a charge and disperse it much better than this small square. In the ground, the charges can run an infinite space between them. So the ground helps the charges really distribute the charge much better. So as soon as the object is grounded, the charges will leave this object and go to the ground, where their charge will be distributed pretty much till it doesn't really matter because it's such a large object. So this object is now neutral. What charges the ground? You could say negative, but remember the ground is so large that those negative charges are really, they don't matter, and also they'll be transferred into something else that you can't even see. So the ground is just neutral at this point. The ground stays neutral. Now let's talk about this item. This item has no electrons, it has 4 positives, so this is a positively charged object. If we touch it to the ground will make the object neutral but in a different way. This time the electrons will travel up and go into the object. 4 electrons will go up here, and now this object becomes neutral. So electrons travel up. On this one, 4 electrons travel down. And as you can see, the ground is always exchanging electrons, so the ground is always neutral. And also it's so much bigger, like I said, that it doesn't really matter if it gains 4 electrons or not. And so the ground is always making things neutral in general. Here is an example where the ground might actually make something charged. This object has been made polar by this, let's say, Van de Graaff machine here, by this positive object. So this positive object has been brought close. All the electrons have run to the left closest to the positive side. and has left the positive protons in place, leaving this side more positive. So now we have a polar object. It is not charged yet because there are 4 positives and 4 negatives, but it is polar. Now in this case, if we touch the ground, this object with the positive side here, it really wants electrons on this side. It's not neutral, so it's actually going to pull up electrons. It's going to pull up electrons. So let's say these electrons, let's say it pulls up 4 electrons. And in this case now we have more negative electrons than positive protons. Now at this point, if this circle were to move away, these electrons would go back into the ground. So it is reversible at this point, and of course these electrons would go back to the protons, and we would have a neutral object that was not polar. But if we were to cut this ground, the electrons could not flow back, so it is no longer able to go back and forth. It is now permanently negative. So in this way we've used the ground to actually charge an object. Now if we move away this positive, this item is permanently negatively charged. It is not polar anymore. So this is one way that the ground can actually be used to help charge an object. But like I said, usually the ground is thought of as a way to neutralize objects. Here's the most famous example for a ground being used. It's used often to protect houses and buildings. A metallic bar is basically put into the ground. It's called a grounding rod. It's put deep into the ground, and at the top, for example, you have a lightning rod. So if the lightning hits this building and it doesn't have a lightning rod, the lightning will go into the building, melting the copper wires, could damage a lot of objects in there, could hurt people. But if you have a lightning rod, the lightning will hit the rod and it will be grounded to the ground, and all of the charge from the lightning will be dispersed into the ground. Now I should say ground does not have to be the ground. It just has to be something much, much larger than whatever the charged object is. So if there's a can and it gets a charge on it, the human being itself is big enough to absorb that charge. So if a human being touches the can, it's going to absorb those negative electrons, for example, and it doesn't really hurt the human. So in that case, the human was the ground. One of the more famous ones is a battery for a car. The battery is always connected to the chassis of the car, which is a huge metal structure around the car. And in that case, the chassis of the car is the ground for the usually 12-volt battery in the car. So my point is the ground is often the ground, but it can also be just anything that's large enough to give or take electrons without really being affected. So in summary, in this video we've reviewed 4 methods to charge an object. We looked at friction, conduction, induction, and grounding.